Okay, hello students. I'm sorry that we're going to have to miss our class today because of the weather, but better safe than sorry, of course. And so what we're going to do is we are just going to kind of plod through. I'm going to give you a recorded lecture today. You'll be able to use this lecture to fill in your notes for Module 8B. So we won't miss any of the notes or anything like this, okay? So if we look at our schedule, you can see that right here is um, today, right? The 1st of February. We're going to be doing 8B physical and chemical change. And then next week, when we get together, we'll start Module 9. Notice Module 9 has 3 weeks to it. Your book is set up for 3 weeks, and so there's no change in the schedule right there. So today I'll show you for our lab, we were going to do a little chemical something and a little physical change something, and the physical change deal will work perfectly with next week. So we should still be able to get in the lab stuff, kind of tack it on to next week so that we don't miss anything. Now, you will still next week have a quiz over Module 8, okay? So I do need you to work on your study guide and be prepared for that next week. All right, so let's get started on our lecture today. Now we are looking at chemistry still. We started that last time. We talked about, elements in the periodic chart of the elements and various things like that. We're going to get a little more detailed this week. Okay, we're going to start off with something called a mixture. So I believe this is going to be your first set of notes in the blanks on your page in your lab book. All right, so a mixture is a substance that contains different elements and or compounds. Okay, so we've taken something and we've mixed it together. That's easy enough to figure, right? If you're making cookies, you would mix the flour and the sugar and the butter and all that together, and you would have a mixture that you would then, of course, bake. If you're making lemonade, right, you would just pour it into the water and you would have a mixture of the lemon powder in the water. So we can also make a mixture that has just elements. For instance, if we wanted to put an element in there and say in a flask of water or something, we could just mix it into it. Normally we would mix something like a compound. For instance, sodium chloride. We can put sodium chloride in the water and make it salty water, right? We can put sugar in water and make it sugar water, and that would be a compound mixture. Whereas an element, it's a little harder to come up with an element. If I took sodium alone and put it in there, do you remember what would happen then? It would just explode. We talked about that last time. It's one of the properties of those in group 1, sodium and those. So, all right. So to classify matter, this is kind of a building on what we talked about last time. We have elements that are composed of one kind of atom. You can see right down here. If I have a helium balloon, it's a balloon filled with nothing but helium, okay? So that is an element of helium. Notice over here I have oxygen. It is an element of O2. And in here we have a compound. So a compound is composed of one type of molecule. In this case, the molecule would be a molecule of water, H2O. So if I had a flask of pure water, anywhere I looked, all I would find would be molecules of H2O. And I'm going to reemphasize that right here. We have the same thing we're talking about right here. What I wanted to emphasize here, that oxygen, notice in both these slides it has them together, and that's because oxygen is a special kind of an element called a homonuclear diatomic. You'll learn about that someday in chemistry. It just means that it travels around sort of like a twin with with another oxygen. It's still pure though. You see, it's still only one kind of atom. Some of the other ones would be hydrogen. It goes around as H2. Nitrogen goes around as N2. Fluorine. Some of the other ones like that. And then, of course, we see water. It's the best example of a compound, right? So it's got H2O. All right, so our compounds contain molecules with chemical bonds. We're looking at a flask over here to the right with a compound. Looks like water is in there. And the bond that happens between the oxygen and the hydrogen. We're going to look at those a little more closely. Here's our mixtures again, composed of at least 2 different elements or compounds, and mixtures can be separated. I'm not exactly sure why the book wants us to have this much repetition, but it's important if I repeat it. Therefore, it's something you probably should know for your quiz next week. Know the difference between a mixture, okay, and a compound, okay? So mixtures can be separated. I believe you might have this a little experiment in your book, which you can try to do if you like. Separating a mixture, for instance, I could have sand and salt together. Those would be two solids that are mixed together, and you can see them in there, the sand and the salt. And the question is, how do I get those separated? Well, one way to do it would be to pour water into a beaker that they are in, and what will happen to the salt? The salt will dissolve and go into the water, leaving the sand alone at the bottom of the flask. So then you could pour the whole thing into another flask that has a sieve right here, a strainer, to catch all the sand, and then I would have down here salt water. So now the question is, well, how do I get the salt and the water separated? That's a harder thing to do, and I bet you already know how we do it. And how we do it is we boil the water away, right? So that if we boil the water away, it'll actually leave the salt at the bottom of the container. You could also leave the container sitting in a warm windowsill, right? And after time, the the water would evaporate away, leaving the salt behind. Some people might say, well, what if I wanted to keep the water? So a way to do that would be if we boiled the flask and had the water turn into a gas, so steam, and then we had that steam hit something, kind of like how we did our making rain in our little beaker, right? We had the watch glass with the ice on top. We would have to have it carried away just a little bit. There's a special kind of a tool called a condensation tube or condensing tube that you can send the steam through and cool it off, and when we cool it off, it will condense back into water. So we actually can separate salt water and have salt in one container and water in another container. It's just not quite so easy as separating a mixture of sand and salt. Okay, so changing matter. We have two kinds of changes. I believe you need to write this down. We have physical change and chemical change. All right, so you can see right here, somebody is using an axe to break a log into smaller pieces. This might be good on a day like today to have some firewood. If you have a fireplace in your house, go cut up some wood and start a fire and have the comfort of that on a cold day. So that's physical change. We're just changing the log to be smaller pieces, more surface area, so that it will actually burn better. But the burning itself, this is called combustion, is an actual chemical change. For a long time, scientists believed that burning happened because of a certain molecule that was, or a certain substance, they didn't even call it a molecule, a substance that was inside certain things, and that substance burned. And as soon as the substance was gone, then it would stop burning. It's, interesting because you can, that some things burn well and other things don't. But it turns out they were wrong about that. And the truth is that burning is a process of a chemical reaction, which requires some sort of fuel, in this case wood, and always, always, always it requires oxygen. And so when we put the fuel, carbon, usually carbons and hydrogens, together with oxygen, and we have to have a spark, it's called an activation energy, we'll get the reaction going. And then, of course, it would burn up the wood and it would change it. Okay, it doesn't disappear, it changes it to heat, light, ashes, smoke, and soot, these kind of things. All right. So this is explaining a little better. A physical change is a type of change in which the form of the matter is altered, but not transformed into another thing. And notice at the bottom there it says a reversible change. So we could say more easily reversible. If I crumble a piece of paper, for instance, I've changed it, and if I flatten it out, then I've got it back. It's reversed, right? But is it exactly the same? No, it's all crumbled now. And that wood that I'm cutting, if I cut the wood up into smaller pieces, I guess I could try to put the pieces all together and hold them together to look like a log. So when we say reversible, we mean it in that general sense, not specifically. Now, but with chemical change, we have a process where one or more substances are altered and changed into a brand new thing. It went from wood to being heat, light, ash, and carbon, and it says here it's irreversible, and in general that is true, but you'll find out someday in chemistry that all chemical reactions actually are reversible, just not very easily reversible. Trying to collect my heat, light, ash, smoke, and reverse it back to the wood, you can see how that's not going to happen. And that's true, that technically that's true. But in chemistry, theoretically, we can reverse chemical reactions. Okay, so now we're going to look at a couple of different scenarios, and I want you to predict whether what I'm showing you is physical change or chemical change. So right here we're looking at some rolls that have been, let's say they're homemade, so I had to let the yeast cause the dough to rise up, and then I put it in the oven and cooked it, so I'm adding heat to it. What do you think? Is it just changing it physically, or is it changing it chemically? The answer is chemical change. Usually when I'm adding heat to something, not always, but when I'm mixing things together and adding heat, oftentimes it ends up being chemical. If I'm just melting something, obviously, that wouldn't be the case. All right, let's see the next one. Here we're just mixing lemons and water into my tea. All right, so that's just physical change. I'm changing it a little bit by adding a little lemon to it, maybe some sugar or something like that. All right, what's happening there? Okay, that's a candle burning. We just talked about combustion, and what did I tell you it was, right? It is a chemical reaction. All right, so that is definitely chemical change taking place on that candle. If you didn't have any oxygen, what would happen to that candle? Right, the light would go out. Okay, this guy's just fixing to mix some cocoa into a cup of milk to make some chocolate milk, although I would say that's not the best cocoa for that. It's not very sweet. That would be physical change. We're just making it from a powder to a liquid. All right, what about freezing water from liquid into a solid? It's pretty changed. It's quite different, but it's still H2O, isn't it? It's H2O when it's a liquid. It's H2O when it's an ice cube. So therefore, it is just physical change taking place there. All right, next we have, bacon is cooking. Remember what I said, if we're going to add heat, it tends to, and in this case is true, be chemical. So chemical change right there. The bacon looks good. All right, so let's talk about chemical change. All right, when we have chemical change, typically what we're doing is we're taking some elements or compounds, or molecules, and mixing them together and doing some sort of change that I end up with something new. All right, so in this particular case, let's see, I have a blank here, right? Chemical reactions are when bonds are broken and or made, and in many cases remade, to produce something new. Okay, so let's look at our reaction here. We have hydrogen. Notice it's H2. Remember, it's one of those homonuclear diatomics that likes to travel around together. All right, and notice we have Cl2 also traveling together right here. This line represents a bond, and that bond represents the sharing of electrons. All right, so we have sharing of electrons between the hydrogens, sharing of the electrons between the chlorines, and when I put these guys together, they're going to want to rearrange. So it's going to take energy to break this bond, and it's going to take energy to break this bond. And then we're going to make a new substance called hydrochloric acid. And we're going to make two of them. That big 2 right up there is to do something called balancing the equation. Whatever I have on this side, I must have on this side. I have 2 hydrogens here, and I must have 2 hydrogens here. Okay, I have 2 chlorines here. I must have 2. This 2 goes to this as well. 2 chlorines here. All right, so I told you it takes energy to break these bonds. It also takes energy to form these bonds. So I have a bond between hydrogen and chlorine and a bond between hydrogen and chlorine right there. So since it takes energy to break the bonds and energy to form the bonds, the question is, which takes more? And when we're looking at a chemical reaction, depending on which takes more, we'll say, 1, how well will it proceed? Can it happen or not? And 2, when it happens, will it be an exothermic or endothermic reaction? And what that means is that it will either produce heat, so therefore let's say we poured it into a flask, the flask will be warm to the touch. It produces heat. That's called exothermic. And that has to do with the bonds on one side having more energy than the bonds on another side. Once again, you'll learn that in chemistry someday. The other one is endothermic. If the bonds breaking on the other side take more energy, then we create something called an endothermic reaction. So in the flask, for instance, I would feel it and it would feel cold to the touch. Those are fun reactions to do. Okay, so right here we're going to make water. So you have a couple of blanks to fill in here. To make water, we need 2 hydrogens and 1 oxygen. Okay, so we're going to see here, I need 2 hydrogens and 1 oxygen, but my hydrogen always travels around as a pair and my oxygen always travels around as a pair. So remember the homonuclear diatomic. So in that case, what I need is I need to have a hydrogen and another set of hydrogens, right? Because these are traveling in a pair. Otherwise, I'm going to have a leftover oxygen. And chemistry doesn't like to have little leftovers. It wants to be balanced, right? Just like a math equation, 2 plus 2 equals 4. We've accounted for everything. There's 2 things plus 2 more things. On the other side of the equation, there are 4 things. Okay, so we have to have the same thing in chemistry. It follows those rules as well. There's a little technicality there. If we end up with excess something, that can happen. But it doesn't follow the reaction all the way through. So right here I have 2 H2 plus 1 O2, and I end up with 2 H2O. There it is. That's our balanced chemical reaction. So I have 2 of the H2s, 1, since there's nothing in front of it, that assumes 1, O2, and I get 2 H2O. And that's a balanced chemical reaction. All right, we have different type of molecules we'll be looking at now. We're going to pay a little attention here to when we set things up, when things move together and become new after we've put them through a chemical reaction or something, or sometimes even a physical change. We can do this. We're going to have different types of molecules. We have crystals that form. We have polymers and plastics that are somewhat of a new deal in the sense that they were discovered in the 20th century. And then we have acid bases. Those are classic reactions, chemical reactions. You know the acid base reaction if you've ever made one of those little volcanoes. The baking soda and the vinegar. The vinegar is an acid. The baking soda is a base. They react together and produce a really, dramatic reaction. All right, so let's look at crystals first. Many elements and compounds form solids that are crystalline in structure. That means they form crystals. They have geometric sides. We're looking at that beautiful purple crystal buried in the clear crystal there. I believe that's amethyst, and amethyst is considered a precious stone or a semi-precious stone. And notice it has a naturally occurring crystal shape. So these cuts along here, that wasn't made by a human. That is the way that the compound built itself. It's pretty cool, the kind of shapes we end up with crystals. This is some beautiful citrine, it's called. It's got that lovely yellow color to it, which citrine, means, orange. So I know that we have a cave in Texas in the Sonora Desert. Well, it's called the Sonora Caves in the city of Sonora, I guess. I'm not sure if that's the desert. That has this special kind of citrine crystal that grows there. It's unique to that one cave in Texas, which I would love to go see someday. Field trip, right? All right, polymers and plastics, those are large molecules made up of smaller chemicals called monomers. A monomer would mean one, polymer means many. Okay, when we link them together in long chains, we discovered they do interesting things. So we're looking at a long chain here. Each one of these little balls represents an element, and the little bar between it represents a bond between those. So probably the dark ones here are carbons. I'm not sure exactly which one we're looking at here. The red ones are probably oxygens, and the white ones are probably hydrogens. So we have a hydrocarbon chain right here, and we can manipulate those, and they turn into some really, really cool things. I think we're going to watch a little video about it here in just a minute. Synthetic polymers are man-made polymers, mostly made from petroleum oils. That is definitely a hydrocarbon substance. So carbons, hydrogens, and oxygens. We call them fossil fuels because they probably came from bones of old animals or something like that. So we put them through a bunch of chemical reactions and we end up with these plastics. You can see here we have different pellets with different colors, and those pellets can be used to make various things. Look around you right now. I'm sure you're looking at many things made of plastic. So now we're going to see that video about it.
Today, plastics are everywhere. All of this plastic originated from one small object that isn't even made of plastic. For centuries, billiard balls were made of ivory from elephant tusks. But when excessive hunting caused elephant populations to decline in the 19th century, billiard balls makers began to look for alternatives, offering huge rewards. So, in 1863, an American named John Wesley Hyatt took up the challenge. Over the next 5 years, he invented a new material called celluloid, made from cellulose, a compound found in wood and straw. Hyatt soon discovered celluloid couldn't solve the billiard ball problem. The material wasn't heavy enough and didn't bounce quite right, but it could be tinted and patterned to mimic more expensive materials like coral, tortoiseshell, amber, and mother of pearl. He had created what became known as the first plastic. The word plastic can describe any material made of polymers, which are just large molecules consisting of the same repeating subunit. This includes all human-made plastics, as well as many of the materials found in living things. But in general, when people refer to plastics, they're referring to synthetic materials. The unifying feature of these is that they start out soft and malleable and can be molded into a particular shape. Despite taking the prize as the first official plastic, celluloid was highly flammable, which made production risky. So, inventors began to hunt for alternatives. In 1907, a chemist combined phenol, a waste product of coal tar, and formaldehyde, creating a hardy new polymer called Bakelite. Bakelite was much less flammable than celluloid, and the raw materials used to make it were more readily available. Bakelite was only the beginning. In the 1920s, researchers first commercially developed polystyrene, a spongy plastic used in insulation. Soon after came polyvinyl chloride, or vinyl, which was flexible yet hardy. Acrylics created transparent, shatterproof panels that mimicked glass. And in the 1930s, nylon took center stage, a polymer designed to mimic silk, but with many times its strength. Starting in 1933, polyethylene became one of the most versatile plastics, still used today to make everything from grocery bags to shampoo bottles to bulletproof vests. New manufacturing technologies accompanied this explosion of materials. The invention of a technique called injection molding made it possible to insert melted plastics into molds of any shape, where they would rapidly harden. This created possibilities for products in new varieties and shapes, and a way to inexpensively and rapidly produce plastics at scale. Scientists hoped this economical new material would make items that once had been unaffordable accessible to more people. Instead, plastics were pushed into service in World War II. During the war, plastic production in the United States quadrupled. Soldiers wore new plastic helmet liners and water-resistant vinyl raincoats. Pilots sat in cockpits made of plexiglass, a shatterproof plastic, and relied on parachutes made of resilient nylon. Afterwards, plastic manufacturing companies that had sprung up during wartime turned their attention to consumer products. Plastics began to replace other materials like wood, glass, and fabric in furniture, clothing, shoes, televisions, and radios. Versatile plastics opened up possibilities for packaging, mainly designed to keep food and other products fresh for longer. Suddenly, there were plastic garbage bags, stretchy plastic wrap, squeezable plastic bottles, takeaway cartons, and plastic containers for fruit, vegetables, and meat. Within just a few decades, this multifaceted material ushered in what became known as the plastics century. While the plastics century brought convenience and cost-effectiveness, it also created staggering environmental problems. Many plastics are made of non-renewable resources, and plastic packaging was designed to be single-use, but some plastics take centuries to decompose, creating a huge buildup of waste. This century will have to concentrate our innovations on addressing those problems by reducing plastic use, developing biodegradable plastics, and finding new ways to recycle existing plastic. So where do you come in? Visit ed.ted.com/end.
Okay, so y'all get the idea here. So science makes life better, right? Better living through chemistry. So I agree about the plastic waste situation. I've tried, and just personally, to try to decrease my use of throwaway plastics. For instance, I bring my water in a cup instead of bringing a plastic water bottle, that kind of thing. Um, Notice this last picture we're looking at here. These are microorganisms that we're working on to eat away at plastic and other, even like oil spills on beaches and stuff like that. So, so once again, while chemistry or science might create a problem, we can use chemistry and science to fix that problem. So it's really quite, useful. And remember, I told you last time that if you get a degree in chemistry, that you'll find a job very easily. Everybody needs a chemist, and you can see right here we need someone to help develop this deal. I think we have been working on a microorganism to eat away at, I know, oil spills on beaches. I know that for a fact. But about the plastics, I don't know that we're quite there yet. So finding something to do that would be really, really great. Okay, acids and bases. We're going to look at kind of the properties of acids and bases. Okay, acid foods tend to taste sour. I will tell you, never taste anything in science class unless you're instructed to do so. But I also will tell you that chemistry is in the kitchen and we taste things all the time. And you think about it, many of the things we like to eat are sour tasting. We're looking at a picture of a lemon right there, and we know it's sour tasting. Also, what acids do is that they conduct electricity when mixed with water. Because they are, see that little thing, it says a H plus donor, that is a hydrogen ion. And what that means is the hydrogen that only has one proton, we learned that last week, one electron, will give the electron away or leave the electron where it was. For instance, if it was with hydrochloric acid, HCl, it'll leave the electron with chlorine, giving chlorine a negative charge, that's a negative ion, and the hydrogen would be a positive ion. It's a donator. That's the reason why HCl is an acid, because the H separates from it, leaving its electron behind. And so a hydrogen ion donator is one of the definitions of what an acid is. Now down here we'll see once again the sour taste. This thing right here, it says, turns blue litmus paper red. Okay, a little explanation there. Litmus paper is a special kind of science paper that has been impregnated with a chemical, and the chemical changes color in the presence of acids. Okay, so it's blue when you start. If you touch it to a lemon or something else acidic, then it will turn pink or red. Okay, so it's just it's called an indicator. And indicators change in the presence of something, and in this particular case, it's changing in the presence of an acid or a base. Acids will also react with some metals to produce hydrogen gas. Right here, hydrogen gases. You've probably seen, I don't know, a cartoon or a movie that shows somebody throwing acid and it like burns, melts a table or melts something like this. There are strong enough acids to do that. They can do that. We don't use those in ODA, so we don't have to worry about it. But there are times when we'll use strong chemicals, especially in my chemistry class, and students have to wear gloves and goggles, and we have to be prepared if anybody gets a spill to get, I have a bucket, remember my douse bucket, for people washing up if they should spill some on themselves. So when it does that, it tends to release some carbonate salts, releasing CO2 bubbles. And so my chemistry class, for instance, we put acid on a little piece of metal and it starts to bubble and it eats away at the metal, which is pretty fun. All right, so if we have acids, let's look at bases. Bases are always going to react with an acid to have a really fun reaction like your little, volcano thing. Bases taste chalky and bitter, and they're slippery to the touch. They are going to take that hydrogen ion from something, from the HCl, for instance, and that's one of the definitions of base. They will receive a hydrogen ion. All right, so the bitter taste right here. We're looking at a bar of soap. Many things we use for cleaning are typically bases. The reason is many messes we make are typically acids. And if I have an acid, the best way to clean it up is to mix it with the base, which will oftentimes do something called neutralization. It will neutralize the acid. It'll no longer be acidic. When you add vinegar to baking soda, the vinegar will not be as acidic because the baking soda would have neutralized it in the reaction right there. Okay, I don't know if you ever tasted baking soda, but it does have a bitter taste. Don't do it unless instructed to. And here we see turns red litmus paper blue. Once again, we're looking at a type of litmus paper that has a certain chemical on it. And this one, it starts red. You touch it to something basic, or another word for basic, by the way, is alkaline. And if I touch it to that, it'll change it to a blue color. Notice it says slippery to the touch. Obviously, that soap right there would be slippery, right? I don't know if you've ever thought about it, but the reason it's slippery is because it is basic. If you've ever been helping your mom with laundry and you were using Clorox, which is bleach, and you poured some in, and afterwards you said, oh, there's something slippery on my fingers, well, that's the bleach and you need to wash it off, okay, because that's a strong base. So we talk about strong acids melting things. Well, strong bases can melt things too. So we have to be careful with both of them. Furthermore, you can think about soap. If we get soap in your eyes, it hurts, right? You think about acid would hurt getting in your eyes if you splash lemon or something. Well, so does a base. All right, and the acid-base reaction, of course, would take those things and put them together. All right, let's watch a little video about it.
From the tangy bite of a piece of fruit to the caustic liquids used to clear a clogged sink, acids are a type of chemical that can be found in many different aspects of our daily lives. But what is it about acids that makes some safe to eat and others dangerous? When talking acids, we're going to be talking hydrogen. Not the gas, but rather the hydrogen ion H+. This is a hydrogen atom that has lost its one and only electron. All acids produce H+ ions when dissolved in water, but it's how much H+ a specific acid can produce in water that will determine whether it can be safely eaten or not. But how do we conceptualize and measure H+ concentration? Søren Sørensen, a Danish chemist, pondered this question when he worked at the laboratories of a commercial brewery in Copenhagen. It was in 1909 that he developed a method of quantifying acidity, what is now known as the pH scale. His scale works by simply converting the concentration of hydrogen ions in a solution to a number between 0 and 14. If a chemical is acidic, then its pH will always be below a 7 on the scale. The lower the number, the higher the hydrogen ion concentration. The pH scale is a logarithmic one, meaning that 1 unit difference on the scale, say from 3 to 2, means a 10-fold difference in H+ concentration. But 0 to 7 is only half of the picture. So what about all these numbers above 7? Substances that correspond with this half of the scale are called bases, and they are the chemical opposites of acids. The 7 on the scale represents neutral pH, what would be perfectly pure water. Like acids, bases are found in chemicals that we encounter in our everyday lives. Cleaning products such as ammonia and baking soda are bases, as are some simple medicines like milk magnesia. They're bitter to the taste and often slippery to the touch, kind of like soap. Even though bases are different than acids, they too can be strong or weak, and a strong base can be just as dangerous and corrosive as a strong acid. Chemically, the difference between acids and bases is that acids produce hydrogen ions and bases accept them. In water, acids produce H+ ions and bases produce OH- ions. In reactions between acids and bases, hydrogen ions will react with hydroxide ions to make water. This type of chemical reaction is called a neutralization reaction. Acids and bases are also very important in biochemistry. Many biological processes are sensitive to the pH of the surroundings, so controlling acidity in the body is crucial. Some biologically important molecules like amino acids have dual personalities. They're said to be amphoteric, which means that they can act as both acids and bases. An amino acid has a carboxylic acid group that can produce hydrogen ions, and an amino group that can accept hydrogen ions. Acids and bases are all around us, and can vary greatly in terms of their use and their nature, but they all involve hydrogen ions being passed around. Thanks for watching. If you
Okay, there we go. That's kind of a summary of all that right there. Okay. All right, so they mentioned on there the pH scale. So notice how that's written, lowercase p and uppercase H. Now, that's important because what is the H representing? It's representing the hydrogen ion, okay? So that P, this is way over simplifying it, but kind of like the percentage of hydrogen or the parts of hydrogen that are in there is kind of how it goes. For whatever reason, Mr. Sorensen made his scale so that acids were down here on the low numbers and bases were up here on the high numbers. I believe that is, arbitrary that he picked it that way. It's kind of weird to think if it's very, very acidic, it has a low number, so it's giving away lots of hydrogens. Okay, so let's take a look at some of these. I don't know if possibly in your book you may have to copy down a few of these, yeah? Okay, so look at pH of 1. That is the most acidic. Look what is the most acidic. Gastric acid. That's the acid that is in your stomach right now. That's called hydrochloric acid. If I took a drop of it out of your stomach and placed it onto your skin, it would burn your skin. That's crazy, right? Because, why doesn't it burn your stomach? It's, made of tissue as well. It's because the stomach is so beautifully designed that it's covered with thick mucus, and that mucus protects it. Why in the world does the stomach have to be so acidic? Well, we're putting a bunch of stuff into it we need to break down, all the food that we need to break down. And of course, the stomach acid and the movement of the stomach, also having chewed the food, right? Because that broke it down a little bit. We have physical change, chewing the food. We have chemical change, saliva and acid in the stomach. And we'll start the digestion process. So that is cool that we are looking at biochemistry right there. Okay, we can see lemon juice, very acidic. Apple juice, none of this is surprising. Did you know that coffee was acidic? Because it's interesting, especially if you drink black coffee that has no, cream in it, it seems kind of bitter to me, right? But it is actually acidic. Milk is acidic, that makes sense. Lactic acid, right? Pure water is neutral. Our bodies like to be sort of in this area right here of neutrality. Bringing us back to the stomach there, since there's a lot of acid there, the rest of our digestive tract uses chemicals to neutralize the acid coming out of the stomach. We have digestive juices coming from the pancreas and from the liver and things like that to make that acid not quite so strong anymore once it gets to the intestines. Over here on the basic side, or the alkaline side, we can see eggs, baking soda, we know about that. Soaps, ammonia, bleach, and here we can see some very high concentrated bases that we would use in a science class, for instance, in chemistry and things like that. Sodium hydroxide is a famous one that we use during chemistry class. Okay, so notice we really like to eat acidic things. They taste better to us. Y'all probably like those Sour Patch candies or whatever, right? I'm going to go back here just for a second to say that some foods are naturally acidic. We see those on the left side. There are some foods that are naturally basic or alkaline as well. And I'm trying to think about something that maybe tastes bitter. I believe Brussels sprouts are somewhat alkaline. And I remember having a picture up for another class, and there were some surprising things. I think bananas were slightly acidic, which seems strange. They don't seem very acidic. Obviously, an orange or a lemon seems acidic. But anyway, we use the pH scale all the time. So our lab time today would have been testing some things using pH paper. So we see that over here on the picture. This is a special kind of a paper. It's not litmus paper. I would have brought that as well. But it's called pH paper. And what's nice about it, it doesn't just change color. It changes color to a certain spot to tell you exactly what the pH is of a substance. Okay, so you can see right here, the paper starts as one color, and I dip it into something, and you see it turn to like a level 2, which would mean whatever that dipped into was acidic. This one looks somewhat neutral, sort of like the 6 there, but look at that one. That looks very dark, very basic, very alkaline. And so we would have been using that today. We would dip the paper into certain things. I would have brought, various things, coffee, lemons, that kind of deal. So that would have been our chemical reaction that we took place, not reaction, but chemical study of the acidity of something. But I also was going to do about physical change. I have these film canisters, and we put a little something into them, and we can cause them to react. But it's only a physical change. So, like I mentioned, it would be perfect for next week when we're talking about motion, when we're looking at Newton's laws of motion. And so I will just use it then. We'll have to, of course, wear goggles and be safe on that. Okay, gang, so that's it for the lecture today. So I hope you got all your notes filled in. If you have any questions, write those down for me. And when we get and you can email me if you have a question that I need to answer. I'll email you back. But other than that, we'll get together next week. We will have a lecture and then a lab as well. Okay, stay warm out there. See you soon.